All right, so this is the first recorded video of the semester, and we're going to jump right in and start discussing how compilers work internally. So the topic of this video is scanning and lexical analysis. I showed you a picture of how a compiler is organized in the first class, and it looked something like this. We have the front end that takes in the C or C++ source code. It checks the code for errors, changes the code into an intermediate representation, and passes that to the optimizer. All right, and last time I showed, in the figure I showed you before, there were multiple front ends, one for each language. Here I've just consolidated all of those different front ends down into one box. And the question I want to deal with is how does this front end work? Now this isn't really going to be the main focus of the class, but I want you to have a sense for how it works so that you understand what's going on inside of a compiler up to the point that we generate IR. So the front end is really made up of several different types of analyses working together. If you look at this box here, I've broken down the front end into three parts. The first part is we need to translate the high-level language, like C, into data structures that we can analyze. Once we've translated into some kind of data structure, then we can perform a semantic analysis of some kind to make sure that that program is meaningful. And then if we wanted to, we could perform front-end optimizations. And what we're going to talk about today in this lecture is part of this first box, translate the high-level language to data structures. And the way we do this is divided into two parts, scanning and parsing. With scanning, you figure out the keywords, the white space, the identifiers, and the punctuation. And with parsing, you prove that the sequence of keywords and identifiers that the programmer wrote are actually meaningful and a legal program. Okay, so lexical. What does lexical mean? It means of or relating to the words or vocabulary of a language as distinguished from its grammar and construction. So if we were interested in the lexical properties of a language, we're only interested in its words and punctuation. We're not interested in whether or not we're putting the words together in a meaningful way. And so the first part of a compiler is typically called lexical analysis or scanning. I'm going to use both of these terms interchangeably. So with lexical analysis, all we care about are the smallest little components of the language, identifiers, punctuation, operators, and we want to break an input source file down into a sequence of tokens, and these tokens are in fact the keywords and identifiers and punctuation. Some examples of tokens would be the for keyword in the C language. That might be a token. The main identifier. Main would be, a name of a function that you would need if you wanted to make a C program. And that function name is considered an identifier in C. And so we'd want a token that specifies identifiers. And then we also have punctuation, like a left brace or a right brace or a left parentheses or a right parentheses. One thing to note here is that comments in white space usually never become tokens. They're never considered part of the language. They're just discarded in the very early stages of compilation. So we do need to handle comments because we don't want to consider them in this analysis, but we're basically just going to handle them to the extent that we're going to throw them away. So we're going to take a C input file, and we're just going to make sure that it's made up of valid tokens. That's the very first step of compilation. So let's look at this C function called foo. Foo takes an integer argument, It checks to see if it's 0, and if it's 0, it returns 1. And if it's not 0, then it multiplies its argument x times the result of calling foo again with on x minus 1. And in fact, if you look at this code and you think about it, you realize this is basically a function implementing factorial. It calculates the factorial of whatever integer value you pass into it. Okay, so what are the tokens of this program? Well, the very first token, and when we break a program down into tokens, we're going to start in the first line with the first character. In the same way we read from left to right, we're going to tokenize a program from left to right, one line at a time. So the very first token would be the int token, and int is an identifier. So the first token is an identifier. The second token is the identifier foo. Now, you might say, why aren't we saying the tokens are int and foo? Well, we don't want to make a token for every possible variable name or function name that could show up. So we're going to represent anything that can be named by the programmer is going to be represented by a single identifier token. However, when we have things like syntax and punctuation, like an open parentheses, then this open parentheses will be its own token. So L paren, left paren is a token. We have another int identifier. We have another identifier for x. And now we have a right parentheses. And then we have a left brace as the next token. We have the if keyword. And since if is a special keyword in the C language, we're just going to make a token represent it explicitly. And the reasons for this will become clear as we go, right? But if is not the same thing as an identifier. An identifier is a name provided by a programmer, whereas if is a keyword that has a very specific meaning. So it gets its own token. Now we have another left paren. Now we have the identifier x inside the if expression. We have the equals to operator. Note that I don't break up the two equal signs into two different tokens, right? They have a meaning when they're placed together. They mean something special when placed together. They mean something different if they're separated individually. So it's really important that when I'm specifying tokens, that I retain the meaning of the language when I specify the token. So these two equal signs need to go together and be recognized as a single token that means equals to. And now we have an integer 0, then right paren, we have the return keyword, then we have another integer, in this case 1, then we have a semicolon, then we have another keyword return, then another identifier x, then the multiply operator, then the identifier foo, then a left paren, identifier x, a minus sign, integer 1, right paren, semicolon, right brace. Okay, so these are the tokens that are in this C program. And so we want to be able to validate that when somebody writes a C program that's made up of legal tokens. And in this program that I wrote, they're all legal tokens. This is legal C code. And right now, I don't care if these tokens are in a reasonable order or if it makes sense. I just want to make sure that the code is made up of legal tokens. So these are the tokens. Now, how do we think about what should be a token, and how do we specify what a token really is? Right? I've said that int is an identifier, foo is an identifier, and that a parentheses is its own token. But we need to think about this a little more deeply and think about how do we actually tell the compiler, what a token is, and what are all the ways a token might be expressed within the code. because anything that's legal to write in a C program has to be represented by at least one token that we want to try to identify when we're reading in the source code. And the way we're going to do this, the way we're going to specify the tokens we want to find in a program is using regular expressions. Now, I expect a lot of you have seen regular expressions before. So I'm not going to belabor this point too much. I'm going to briefly introduce them. There are a lot of online resources that can tell you a lot about regular expressions. So there's something you don't know a lot about and you're still confused after this video, I encourage you to go out there, find some online resources, and maybe even post the links you find to Piazza so other students can benefit from it as well. Okay, but a regular expression is a way of representing a set of strings in a concise way. And when a string is described by a regular expression, it's said to match. So now we're going to look at some regular expressions and the strings that match the regular expressions. The simplest regular expression you can have is a single character that simply represents itself. It matches itself. So for example, if the regular expression is the character A, then the matching string is the letter A. If the regular expression is B, then the matching string is B. If the regular expression is 1, then the matching string is 1. If the regular expression is the semicolon, then the matching string is the semicolon. Right? So this regular expression is very simple, and it has exactly one matching string in this case. So if we want to specify a semicolon token, we're going to use a regular expression that is just a semicolon. And that will let us match semicolons in the C code, and we'll know because I have a token that says I'm allowed to find semicolons in a C program, then when I find it in the code, I'll know that it's okay, that it matches a regular expression specified for the language as a legal token, and I know that the code is at least made up of, that at least that a semicolon is a valid token. Okay, but single character regular expressions aren't really that useful. We're not going to get very far. So you can put two regular expressions together to match more interesting patterns. So if my regular expression is AB, then I can match the string AB. Or if it's AA, I can match the string AA. Or perhaps in a more useful sense, if my regular expression is IF, then I can match the string for if. And you're not just limited to two regular expressions, right? We could append together as many regular expressions as we want to match much longer strings. So if I want to match the keyword for, then I can have the regular expression FOR, and that will match any string that is made up of the letters FOR. Okay, and likewise for the do keyword in C as well. And I'm not restricted to just alphabetic characters. I can also match symbolic characters like the pointer access operator in C, which is made up of a minus sign followed by a greater than sign. Right, so I can specify this as a single token, and any string that's a minus followed by a greater than is going to match that regular expression. Okay, now, so far we can append regular expressions together, but sometimes what you really need is to be able to say, I want to match strings that are either this or that, right? You need to have some flexibility in what you're matching, and this is especially true when we start thinking about identifiers, right? Because there's not just one identifier in a C program or one number in a C program. There could be lots of different identifiers. And part of doing that is using the alternation operator. The alternation operator is represented by a bar. It looks like the bitwise OR in the C language. But in the case of regular expressions, it just means choose this or that. Choose A or B. And since you can choose A or B, then the matching strings are the string made up of the letter A and the string made up of the letter B. And I can expand on this, and I can say I could have a regular expression that the string AA, or the string BB, or the string AB, or the string BA. And then the matching strings for this regular expression would be AA, BB, AB, or BA. Now that last notation is kind of long, and you rarely want to have to write out all possibilities. So we can do something a bit smarter. And we can say, you know, rather than specifying all combinations of A and B, let's write it more succinctly and say that first pick A or B, and then pick A or B again. And so the parentheses specify a unit that should be evaluated separately from the rest of the expression. So in the first parentheses, pick A or B, and then in the second parentheses, pick A or B again. And so that's going to lead to the same matching strings. I can pick A in the first, followed by A in the second parentheses, or I could pick B in the first and B in the second parentheses, or I could pick A then pick B, or I could pick B then pick A. And those are the possibilities. Okay, similarly, if I wanted to represent all the numbers, I could say pick 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 0. And this would let me specify all the strings that match a single digit decimal number. Something that relates directly to the C language, maybe I want to concisely specify all the combined assignment operators. So I could say pick, plus, minus, multiply, divide, and then append an equal sign. And so that would match plus equals, minus equals, times equals, or divide equals. Okay, now in some cases, it's really inconvenient to write out a bunch of options. Like earlier when I specified all the digits 0 through 9, I had to write them out, and that's really tedious. So what we often do instead is to specify a range inside brackets. So these brackets mean you're only going to pick one, right? But you can pick anything from the range A to F. And usually when we talk about regular expressions, you know, it's understood that there is a well-defined sequence of letters from A to F, and you know we all know what they are. And so if we just say A-F, it means everything between A and F, and you can only pick one. And so this notation means that it matches all the strings from A to F. So A, B, C, D, E, and F are the ones it specifies. Similarly, if I wanted to, I could specify hexadecimal digits this way, right? I could say that I want to pick one from the set of numbers made up of 0 to 9 and A to F. And so then my matching strings would be any single digit string from 0 to 9 inclusive and A to F inclusive. Okay, so alternation plus this bracket notation is very powerful for representing a range of things very concisely. Okay, now the other thing we need to be able to write some really nice regular expression patterns are operators that imply repetition. So far, if we want multiple numbers or multiple letters, we have to write them out and append them. That gets old really fast if you're specifying a lot of regular expressions and a lot of interesting patterns. And so we add some additional notation that lets us specify how many times to match. So in regular expression notation, a star means match 0 or more times. A plus sign means match 1 or more times. And a question mark means match 0 or 1 time. Okay, now we can do some more interesting things. Before we go on, one thing to note on this previous slide is that a star means I can match 0 times, and a question mark can match 0 times. Well, what does it mean if a string, what does it mean for a pattern if you say you don't have to match anything, right? You're matching 0, you're matching nothing. Well, it means that you can match an empty string. And so if a regular expression can match an empty string, we're going to state that explicitly using the little epsilon. And so if a regular expression can match nothing, I'll put an epsilon in the list of matching strings. If it can't, if it always matches something, then you won't see an epsilon there. So for example, for the expression a star, it could match nothing at all. So it could match the empty string. But it could also match 1A, it could match 2A's, 3A's, 4A's, up to an infinite number of A's. Right, so this is an infinite number of matching strings for this regular expression. For A plus, on the other hand, plus means match one or more A's. So the empty string is not included here, and it can only match a single A, 2A's, 3A's, 4A's, 5A's, and so on, all the way up to an infinite number of A's in a row. Okay, coming back to my earlier example where I said you could pick A or B once and then pick A or B again, we can generalize this, and we could say you can pick A or B 0 or more times in sequence. So this is made up of the string, the empty string, a single A, a single B, a combination of two, all strings of length 2 that are made up of A's and B's, then all strings of length 3 that are made up of A's and B's in any order, followed by all strings of length 4 that are made up of A's and B's in any order of any order, right? And on up to length 5, length 6, length 7, and so on all the way to infinity. Okay, now you probably never want to specify a string made of A's and B's, it's just not all that interesting, but you might want to specify all the strings that can be a number. Right, so maybe we want to say you can pick a digit from 0 to 9, and then match that one or more times. Okay, now that's nice because now we very concisely stated all of the integers that could ever be written in our C program. Right, starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, as big as you would ever want to go. And they'll match this regular expression. Okay, now the question mark is kind of a funny one. Right, if I write the expression a question mark, it means matches 0 or 1 time. So that means the matching strings for this expression are the empty string and the letter A. Why would this be useful? Why is it useful to have a question mark? Think about that for a minute. Well, there are a lot of things in programs that maybe can happen no times or 1 time, but not more than 1 time. For example, a decimal point in a real number, or for that matter, the leading 0. So in this last example, I'm saying a fractional number can either have a leading 0 or not have a leading 0. So it might be 0.1 or 0.1, 0.2 or 0.2, and both of those would be legal. So that question mark allows us to say that the 0 is optional. Okay, so let's represent the tokens some of the tokens we've talked about already and that exist in the C language with regular expressions. So if you want, pause the video, sketch out some answers on your own, and then resume when you have some of your own answers and you want to take a look at what I did. I will say that for some of these, they're, in particular for the real case, it's to match real numbers for C programs in a fully correct way is really sophisticated. And so I'm not going to show you that answer on the next page. So, don't try to work out all the details of exactly representing real numbers, but sketch out an approximation. Okay, so let's take a look at identifiers. If you remember from your own experience programming C or from studying the C language, a C identifier can begin with an underscore, a lowercase letter, or an uppercase letter. And so when we specify the token for identifier, we're going to specify that the first character of the identifier name has to be underscore or a letter. But then all additional characters, if present, can either be underscore, a lowercase letter, an uppercase letter, or a digit. but you're not required to have more than one character. So the first set of characters, the first character has some restrictions, but the second and additional characters do not, and they're optional. So we specify a star to indicate that we might get one of these characters, but we might not. So right, the first character has to be either an underscore or an uppercase or lowercase alphabetic character, and then the remaining can be an underscore, an alphabetic character, or a digit. Okay, now what about a number, an integer number? Well, an integer number can begin with a plus or minus. Now the reason if you look at my syntax here, the reason I'm putting backslashes on the plus and minus are because plus and minus have special meaning within my regular expression. And so that it's not confusing as to what they mean, right? They're not regular expression operators. I actually want the actual plus and the actual minus character. Then I put a backslash to mean that I'm, as an escape character, like you would in C if you wanted to print out a new line, or if you wanted to, print out, quotation marks. You need to specify that no, you don't want the language's meaning of that symbol. You want to refer to the actual symbol. And so this just means I actually want a plus sign, I actually want a minus sign. I'm not using them to mean one or more or to specify a range. Right? So we're going to have some sort of sign, but that's optional, so I specify the question mark. So I'm going to pick a plus or a minus, and then that plus or minus may not be present. Then we have a sequence of numbers made up of the digits 0 to 9, and I can have one or more of them. Right? Or I could have a hexadecimal number, maybe, that begins with 0x, and then made up of the digits 0 to 9, A to F, or capital A to F. And I'll have one or more of those. Okay, so in my specification of number here, I can support plus and minus, I can support any length decimal number, and I can support optionally any length hexadecimal number, but if I match a hexadecimal number, it has to have this 0x at the beginning. And I can only either match this or this. I can't match both. Okay, it might be, now that I'm looking at the code I have here, it might be you need to add some extra parentheses in here. You might need some parentheses around the 0 to 9 plus and parentheses around the 0x. Followed by the expression for the numbers, right? So I may not have enough parentheses in that, but hopefully you understand. Hopefully understand the meaning of that regular expression. Okay, real gets quite a bit more complicated. I've preserved the plus and minus that's optionally at the beginning of the real number. Okay, then I'm going to have a digit from 0 to 9, possibly, one or more of them, followed by a decimal point, followed by another set of digits from 0 to 9, one or more of them, then followed by an exponent. And then the exponent can have a plus or minus, and actually I left off the question mark here, so there should have been a question mark on the plus or minus, followed by some number of digits, one or more. And then this exponent is optional. So I've put this whole thing in parentheses, followed by a question mark. You might have come up with something different. You might have come up with something better. This isn't exactly what you would implement for C, but it contains a lot of the elements that you would need. You need to be able to support plus and minus. You need to be able to support digits before and after the decimal point. You need to be able to support an exponent. But in the real C language, you'd also need to support little e. You would also need to allow for numbers that don't have a leading 0, so it would be perfectly legal to say minus 0.1 without the 0 before the decimal point, whereas my specification does not allow that. And so if you really start thinking about what you're able to do in C and what this regular expression allows, you realize it doesn't cover everything. It needs to get a lot more complicated to cover everything that's legal in C. Okay, if, this is a simple one, it's just if. Comma is also a simple one, it's just the comma. And then not equal is a simple one, it's just exclamation point followed by the equal sign right beside each other. Okay, so we've looked at the pieces of a C program, how we can describe them using, how we can break a C program into tokens, and how we can describe those tokens as regular expressions. Well, if we wanted to implement a lexical analyzer or a scanner, then we would need to write C code that implements all these regular expressions and matches and tries to verify that the input program is only made up of these legal tokens in the C language. Now, if we were to have to implement that code by hand, it would take quite a bit of time to code up all these regular expressions. It's not terribly difficult code. If you took ECU 209 here, then I know you should have a pretty good idea of the type of programming you would need to do it, right? You would need to read in strings into an array. You would then want to compare each character in the string to some character in the regular expression, right, one at a time. And you know, if you went through the effort of hand coding all these regular expressions, you could do it. You could write a lexical analyzer for the entire C language by hand. But this is not the way it's done anymore. It's very rare that you would ever write a scanner from scratch in C code. Instead, what you'll use is a program called a scanner generator, in which you specify a bunch of regular expressions, and then it automatically creates C code for you that matches all of those expressions. So in the next video, I'm going to show you an example of such a scanner generator, how to make an input file for it, and then how to get it to generate some C code for you that will automatically match the tokens of a language. Thanks for listening.